Yes, ma'am.
Yes, ma'am. It is.
Okay, thanks. So, okay. So today we will look at the system of linear equations. So yesterday we were doing a recap and we did some things about subspaces and like null space, the column space, and so on. So today we will see how you will use these concepts, okay, to solve the system of linear equations. So what we're trying to do here is we have a matrix A, so which is of size m cross n. So this is actually characterizing the set of equations that you have. So you have m equations and there are n variables. So the x's are the variables, so that these are the unknown quantities. Okay, there are n of them. And you also have these b's. These are the right-hand side coefficients. So that's given to you. So a and b are given to you, and you want to find an x which satisfies the set of these set of equations. Okay, so m equations, n unknowns, and you want to solve them. Okay, so pictorially, this is what you want to do. So this is Rn, and this is the whole space Rn. So A is this matrix which kind of does a transformation from the space Rn to Rm. So you're given this vector B, this is given, and you want to find this x. Okay, what is the x which takes it from Rn to Rm? Sorry, what's the x which when A acts on, you get B. Okay, so why is this important? So this is actually one of the most fundamental things in optimization. You know, it's important in almost everywhere you will see this. So one reason is that, you know, many of the optimization problems are of this form. So you want to minimize some function and subject to some equality constraints. Okay, so these understanding the system of equations helps you to understand the feasible region. Okay, so that's one of the reasons why this is important. Now, the other thing is that even though you may not have an optimization problem exactly in this form, what happens is that many a time to solve optimization problems, you end up having a characterization. I mean, you'll see this later on in the course, and the characterization will involve some system of equations of this form. So in order to get the solution to an optimization problem, you will invariably end up solving some system of linear equations. Okay, so that's why it's really important to understand this. All right. Okay, so yeah. So now there are some points you need to answer. Okay, so just give me a minute. I just need to step out and be back for a minute. Just hold on. Okay, sorry about that. Yeah, I'm really sorry about the disruption. So I guess the screen is again shared, right?
Yes, ma'am.
Okay, so yeah, so what I was telling is like we are interested in getting the solutions for the system of linear equations. Okay, so now the thing is, if you're given a b for any b, is it always guaranteed that you can find an x? Okay, so yeah, so you never know, right? So many times you have m if it's less than n. Okay, so then you don't know if you have more unknowns but fewer equations. Then you don't know if you have a solution. And even the other case, if you have m greater than n, you have more number of equations than the number of unknowns. So if something is redundant, then maybe you have a solution. Okay, but otherwise you don't know. So these are some of the issues here, and we want to understand that. Okay, so does the system always have solutions? And if it does, how many solutions does it have? Is it a unique solution? Is it many solutions? Is it like infinitely many solutions? What is the deal? Okay, so how do we compute these things? So that's what I would like to focus on for some time now. So now let's answer the first one. Does the system always have solutions? So it turns out that this fact, to answer this, you need to find the column space of A. Okay, so if this B lies in the column space of A, the solution exists. So remember, like yesterday, we were saying that when you multiply a matrix A with a vector X, okay, you can write it as x1 times the first column plus x2 times the second column and so on. Okay, plus xn times the nth column of A. That is one way you multiply these vectors. So if you, now you have B, okay? So if this B can be represented as a linear combination of the columns of A, so that's what it means by saying B lies in the column space of A, then you can find an X. So this is exactly what you're trying to do, right? You're trying to find a linear combination of the columns of A, which gives you B. Okay, so this is what, in theory, that's when you have a solution to the system. Now we will see how you find this. Okay, so now suppose you have a solution. It's guaranteed that, okay, B lies in the column space of A. So how many solutions does it have? Is it one solution, or is it, what is it? How do you analyze this? So this is where the null space is going to be useful. Okay, so now remember, the null space is the set of all x such that Ax is 0. Okay, so the set of all x such that when A acts on it, you get the 0 vector. Okay, so by default, this null space is it's not empty because the 0 vector is there, right? If you multiply A with 0 vector, you're going to get 0. So anyway, this is there in the null space. Now the question is whether there is anything else in this null space. Okay, so other than 0, is there something else in the null space? So suppose you have some V in the null space. Okay, and suppose you somehow manage to find some solution to Ax equals B, and let's call it U. Okay, so I will come to how you can find this U, but for a minute, assume that you have this solution given to you, and you also have an element from the null space. Now, U plus V is also going to be a solution. So why is that? Can someone tell me why that's the case?
Linearity.
Linearity, right. So what you mean by that is, who answered, by the way?
Rohit.
Rohit, okay. So what Rohit is saying is you have A, U plus V. If you do, you're going to get AU plus AV. Okay, and you already know AU is, this is B, and this is 0. So this is also going to be a solution. So U plus V is going to be a solution. And in fact, any multiple of V. So suppose you take U plus 2V, that's also going to be a solution. So in general, any U plus any alpha V, that's going to be a solution for the system. Okay, so you're going to have like infinitely many solutions. Right. So now this is a case when the null space has something other than the 0 vector. Okay. Now suppose the null space only contains the 0 vector, then turns out that the solution is going to be unique. Okay. I mean, suppose the null space only has 0, and of course you have AU equals B. Okay. Then it turns out that you're going to get this is the only solution. So any thoughts on why that's the case?
If you had 2, you could just subtract them, and if they're non-equal, then you'd find another vector inside the null space.
Yeah, exactly. So who was this?
Divyani.
Divyani, okay. So what she's saying is, if you had, say, something else, like A U2 equals B. So then if you did A U2 minus U, okay, so this is going to give you 0. Okay, so this would have lied in the null space, but that's a contradiction. Okay, so these are some of the things you need to know about analyzing the system, like when it has a solution, when does it have multiple solutions, and so on. So now, in order to actually find the solutions, what you need to do is you need to do some operations and to transform A to some alternate form where you can easily tell the solutions. Okay, so an example is this. Suppose you did a transformation, you did some set of operations which will come to soon, and you got a matrix, an equivalent form of this form. Okay, you did some operations on A and B, and this is what you got. So from here, so suppose the variables are, let's say, X, Y, Z, and W. Okay, so the 4 columns, they correspond to these variables, X, Y, Z, W, and this is the B. So from this, you can easily read off the solution, right? So this would be X is 2, Y is 1, and Z is 8. Okay, W, as per this, W can be anything. Okay, it's not specified. I mean, yeah, any value of W will satisfy this, right? So the idea is to, do a transformation to get something close to this, so something of the form like an identity, which has an identity somewhere in between, so that then you can easily, read off the answers. Okay, so let's see how to do that. So for that, we'll make use of this example. Okay, so A is it's a 3x4 matrix. So you have 4 variables here. Again, X, Y, Z, W. So A times this matrix is going to give you this 5, 10, 3. Okay, so yeah, let's see what you can do. So as a first step, so these are, I'm telling you what you do is these row operations. So there's some standard operations, okay, which you will figure out like from this example. So the way you do this is you first write A altogether, and then you write B as well. Okay, and now what I'm trying to do is I'm going to make this row. I want to make it in such a way that there is a 1 here already in the first column. So I want to make these entries 0. Okay, so for doing that, first I multiply the second row by half. Okay, so that will give me this result. Okay, now I just subtract R2 from R1. Okay, I just do this operation. Okay, so R1 from R2. So because I want to make this 0, so this is what I'm going to get. This is actually identical to the first row. And so you get a row full of zeros. Okay, and then everything else remains the same. Now, for ease of, for some convenience, I want these zeros to go to the end of the matrix. Okay, so that's why then I swap them. Okay, so all the rows containing full of zeros, they are moved to the end. Okay, so that I can focus clearly on the first part of the matrix. Okay, so now I only have these 2 rows left. And so here I want to make this as 0. So what I do is, again, I do the same operation, but remember this row is now the swapped row. So I again do R2 minus R1. And what I'm going to get is this result. Okay, so 0, minus 1, minus 1, 0, and minus 2. Okay, so I just worked out this example so that I think you guys are already familiar with it, so it's easier to just go over these steps once. Okay, so please stop me if something is not clear at some point. Okay, so now we have this result, and so this column is clear. Okay, now the next thing is we wanted something like the identity, right? As to the extent possible. So for that, what you do is you multiply this row now with minus 1, because you already have a minus 1 here. So you multiply it with minus 1 to get this. So this is almost done. Now only thing is you have these entries here. So this part is clear. You have a 1 here, and you want to make this one also 0. Everything else in that column, you want to make it a 0. So that's why the operation you would do is R1 minus 2 times R2. Okay, so that gives you this result. Okay, so I think, yeah, is this as best we can do? Is there something better? So with this, is it possible to tell the solutions? Can someone try? So remember, you did the same set of operations. You started with A and B, and then you did the same set of operations on all these entries of A as well as B. Okay, so, and the result you had was this. Okay, so can you, yeah, so now with this, so remember this part was A, so this is the modified matrix A, and this is B. Okay, so with this, is it possible to tell the solutions? Can somebody tell what the revised set of equations would look like? So the variables were x, y, z, w.
Y plus Z equals 2, X plus Z plus W equals 1.
Okay. Sure. And the last one, there's nothing, right? Everything is zeros. So that's what you get here. Okay. So one solution for this. Okay. Can you tell me some solutions now from this? So you need to get the values of x, y, z, w. So
Parameterize solutions. There will not be a unique one.
pardon?
There will not be a unique solution, right? There will be a parameterized solution.
Sure. So can you give me like some, I mean, if it's parameterized, can you tell me a parameterized solution?
0, 1, 1, 0, 1, 1, 0.
0, 1, 1, 0. So here, yeah, this one is satisfied and this one is also satisfied, right? And anything else? Can you tell something else as well? So this was obtained by, like by fixing x equals 0 and y equals 1. And then you compute z and w in terms of x and y. So that's how
0, 0, 2, 0 also.
0, 0, 2, 0.
Oh no, wait, sorry. 0, 0, 2 minus 1.
Minus 1. So 0, 0, 2, 0 will not satisfy this equation. So 0, 0, 2 minus 1, right, that's also a solution. Okay, so you can get several solutions of this form. Okay, so another solution, so for ease, what people usually do is you just fix two of them. So suppose I fix x and y. So x and y, I say x is 0 and y is 1. So I get this solution, z is 1 and w is 0. Now, similarly, I will take x is 0, y is 1. So the reason is you pick two of them because there are two equations here. Okay, so you fix any two of the variables and then try to express the others in terms of this. Okay, so another way to do it is you can have 1, 0. Okay, so then what is z and w? Can someone tell me?
1, 0.
Z is
Z is 1 and W is 0.
Z
Oh,
is
no,
1,
no.
is it? So Z
No, Z is 2.
Z is 2, right? And W is?
Minus 2.
Minus 2, right? So yeah, so the idea is that you can verify that these are going to be linearly independent, these solutions that you get by writing it in this way. Okay, so that's something you should check. And so what you can do is now, yeah, so these are some solutions, and actually there are many solutions, right, for this. So the reason is because the null space is non-empty. It has something more than the zero vector. So that you can understand because when you do this set of operations, the resulting matrix that you get, the number of rows which are non-zero, here this is 2. Okay, so there is one extra element here, okay, which is non-empty. And so the rank of this matrix A is 2. Okay, and remember we spoke of the rank nullity theorem. So it said that the rank and the null space, okay, they have to sum up to the number of columns. So here the number of columns of A is 4. So the null space is going to have 4 minus 2, so 2 vectors. Okay, so it's not, I mean, it has a dimension 2, not 2 vectors, its dimension is 2. So definitely you'll have something more than the 0 vector. So remember the null space is the number of linearly independent vectors in the basis. So basis is the number of linearly independent vectors which spans this null space, right? For if you're saying the basis for null space. And here if you're saying the null space is 2, then there must be something other than 0 vector, because if you have only the 0 vector there, the any basis will have only 0 vector, and that is by default it's a linearly dependent set. So it cannot have a dimension of 2 in that case. Okay. So now if you want to find the null space, what you do is the same steps, but instead of writing these operations for B, what you do is you write it for, taking this as zeros. Okay. So actually it's, you take it as zeros, but if you do these operations that we did for the 0 vector, it's always going to give you 0 itself. Okay, because the kind of operations we did was such. So what all did we do? We did a multiplication. So this part, okay. So multiplying a row with some constant, multiply a row with a constant. Okay. Then you did these kind of operations. So this is one operation you did. Then the second thing you did was doing some additions of rows, or in fact, you could also do any linear combination of rows. So, linear combinations of rows. Okay, and the other operation you did was swapping of rows. Okay, so this swap rows. Okay, so these were the 3 kind of operations that you did. Okay, so these are all belong to one of the categories that we did. And so these are called the elementary row operations. So if you see what is actually happening here, by multiplying a row with a constant, internally you're multiplying some equation with some constant. So that doesn't change the system of equations, right? And similarly, if you if you do something like alpha times equation 1 plus beta times equation 2, okay, that is not going to change the system again. Okay, and similarly, if you swap rows, you're just changing the order of the equations, so that's also not going to change the system. So that's why these are the only allowed operations. And so if you do these, you can somehow get it into a form which you can solve for easily. Okay, so so similar operations now, if you do to get the null space, and where you take B is the 0 vector. So these operations that you did, it's always going to give you, this last part is going to be 0 itself. Okay, so only thing that changes is this A. So actually you will get back the same thing. Okay, without this B, without the last column. And so then you can read off again the solutions for the null space. So that is just, it's the same thing, whatever you did earlier, but you just substitute x plus z plus w is 0 and y plus z is 0. So what are the solutions here? And here also there can be 2 solutions, right? Like the similar approach you did, you can fix the values of x and y. Okay, so can someone tell me? Can someone tell me the solutions here?
So it can be 0, 1, minus 1, and 0.
So 0, y is 1.
1.
Okay.
Z is minus 1.
Z is minus 1, right.
W is 0.
W is 0 or?
1.
W is 1. Okay. So similarly, you could do for the other way, right? X is 1 and y is 0. Okay. So what will this give you?
Z is 0 and W is minus 1.
Z is 0 and W is minus 1. Right. Okay. So this is going to be, the elements in the null space. So if you see the overall system, the set of solutions is going to be something of this form. Okay. I think I probably wrote a different set of elements from the null space. What was it? Yeah, it's the same thing, only these things. So this was the first one, and this is the second one. Okay. So this is going to be the overall solution here. Okay. So one thing to note is that, yeah, here if you, in this revised set of matrix, the revised matrix that you got, whatever rows that you get, okay, so these two rows, that actually is going to be, this is going to be a basis for the row space, okay, for the row space of A. Okay, so that you can get from these. So this is going to be one, it's the rows, right? 1, 0, 1, 1 and 0, 1, 1, 0. Okay, so these two rows are going to give you the row space. Okay, why? Because if you take, it's basically all the same rows of A, which you did some operations and verify that these rows are also linearly independent. Okay, and so that these are the two rows which, if you take a span of this, you're going to get the overall set of vectors in the row space. Okay, so if you wanted to find the column space, the same kind of operations you would do with A transpose. Okay, so yeah, so that's just some detail on how you find these various row spaces, column spaces, and so on, and also the null space. Okay. So, any questions so far? Nothing's clear? It's okay?
No questions.
So you should ask if there is anything. For some of them it's clear, but if the rest of you, I wouldn't know if things are not clear. So don't feel shy to ask. Some of you may follow, some of you won't, but it's perfectly fine if you don't follow. You should ask me. Okay.
Excuse me, ma'am.
Yes.
Can we show the overall solution once again?
Yeah.
Okay, ma'am. Thank you.
Yeah. Okay, so all right. So now, I think now I'll move on to this next topic of vector norms. Okay, so we saw norms in some form yesterday when we talked of orthogonality. So so norms, we usually use them to capture some notion of distance between vectors. Okay, but before that, let's just understand what a norm is. It acts only on a single vector x. So it's basically any function which satisfies these properties. Okay, it's always greater than 0, and it is equal to 0 if and only if x is 0. Okay, and so it's always a non-negative quantity. And if you multiply some x with some r and then take its norm, then what you're going to get is the absolute value times the norm of x. So for example, if you do something like norm of 5x, okay, what you're going to get is 5 times norm of x. So that's just what this property is. And then you also have triangle inequality, which says that norm of x plus y is less than the norm of x plus norm y. So this is actually needed for capturing the notion of distance, because what you would do is, so you have x, and so suppose this is the vector x, and then you're going to some other place, and that's the vector y. So this x, okay, my drawing is very pathetic. So okay, so this is the vector x plus y. Okay, so if you go in this way, this kind of a way, like a shortest way from x, from this point to here, so that would give you this vector x plus y, and that is less than going in this along this route and taking this other route. Okay, so that's what triangle inequality intuitively tells you. Okay, so there are several kinds of norms and an example. So I've just listed some examples here. So the one norm, so x is, to remind you, it's this vector x1 to xn. So the one norm just takes the sum of the absolute values of the components. Okay. Now the two norm is what you would have most been, you would have been most familiar with, and this is also something which we will use most often. Okay. So this is just defined this way: square root of x1 square plus so on up to xn square. And then there's something called the infinity norm. Okay, so this is the max value of xi. So the max of each of the components you take, that is the infinity norm. Okay, and in general, any p you take, you're going to get this kind of an expression. Just generalize this. So xi power p, and you take all the sums and then just take the pth root. Okay, so these are important because, like when you solve optimization problems, when you try to understand the theoretical guarantees, so many times you're doing an iterative process, and then you want to be able to capture how far you're from the optimal solution. Okay, so that's why these norms are used in that context. Okay, so we'll come to it later. Now, one thing is there are so many norms I mentioned here. Okay, so let's try to understand what these norms look like. Why so many? What are they like? Okay, so for that I will just show you a Matlab script that I prepared. Okay, so to generate these values, so what I'm going to do is I'm going to take some two-dimensional plot. Okay, so two-dimensional set of values, vectors of 2 dimensions, and I'm going to plot the set of all values which have the same norm, a set of all vectors which have the same norm. So for instance, okay, so are you all familiar with Matlab?
No, ma'am.
You're not familiar. Okay,
No, ma'am.
so okay. So I think some of you are familiar, but some of you are not. But anyway, these equivalent things, you can do it in Python also. I think many of you are familiar with Python. So you should explore anyway both the languages. But of course, you're free to choose the one that you like. So I'll just show it in MATLAB here for now. So here what I'm doing is I'm just generating the set of all values. Okay. So I think these mesh grid and those kind of things are there in Python as well. Okay, so what I'm going to do is now I'm just computing so x's are going to take a value between -2 to 2, and y is also going to take values between -2 and 2. Okay, and I've generated all the points here, and I'm just going to plot the one norm. So it's just the absolute value of x and y. Okay, so now let me just plot it. So I'm going to use this contour function. Okay, so let's just try the contour as such. Okay, so contour x, y, z. Sorry, z1. Okay. Okay, so you get a plot like this. So what this is telling you is if you take any of these lines, so you take this innermost line, this is the set of all points. So here you have the x's, x direction and the y directions, and these are the points for which they take the same value. So there are actually, it shows it in different colors. So for each color, that's the set of points which take the same value. So you can just show the labels also. You can show the values here. Okay. Yeah, so you see so this plot, it's the set of all points for which the absolute value, the norm 1 is 1. And this is the set of all points, this large sort of square. It's the set of all points for which the one norm gives a value 2. Okay, so yeah, I leave it to you to figure out why it takes this form. Okay, like why the shape is in this way. Now similar things you could do, okay, for the 2 norm. Okay, so this is the square root of x square plus y square. So let me just show you the contour. So this is going to have a circular form. So this we all have seen, right? Like this is the equation of circle. So each of this is the equation of a circle. So we can just see it clearly with, sorry, with the labels as well. So if you take this blue curve, this is a set of all points for which x square plus y square is 1. Okay, and this is the set of all points for which x square plus y square is 1.5 square. Okay, so so that's like we know from your school days that has to be a circle. So that's why this shape. Okay, so now another thing you can do is you can also look at all the points. Let's take the one norm itself. You can look at all the points for which the norm is 1. So this is a syntactic thing in Matlab. So you only want one curve. So the set of all points for which the norm is 1. So that is just this one curve. Okay. So you can do this. You can just try to see what these various norms look like. And I have this kind of a plot which gives you this visual of you start with one norm and then the two norm becomes a circle, and how the later on norms, how it progresses. So I encourage you all to try out and see what these norms look like. Okay, so yeah, I think these kind of things help you to understand various distance metrics and so on. Now all these norms are equivalent. Okay, so in the sense that later on when you study like optimization problems and how to solve them, it will not really matter which of these norms you use. Okay, they're all notions of distance, but they are they give importance for different aspects. For example, the infinity norm only looks at the max value. Okay, it doesn't care about anything else. So it turns out that for any two norms, there is this relation which holds. Okay, so if you have this p norm and a q norm, okay, for some values of p and q, you can find these values c and d such that the qth norm is sandwiched between these two. So in the sense that if you have some vector x and the pth norm is close to 0, then you're also most likely going to have at some point the later on other norms also will approach 0 soon. Okay, so that's why it doesn't matter like which of the norms you use finally. I mean, of course, the exact value will change for each of these norms, but the relative values across the like x and y, if they have some relation, the norm x is less than norm y, that is kind of going to get preserved across norms. Okay, so that's one thing I want you to remember. Now, this is another point. This is about the Cauchy-Schwarz inequality. This will come again and again. So if you have two vectors, x and y, so yesterday we saw the inner product, right? So what are the values of the inner product? It ranges between, we saw intuitively that x transpose y, you could write it as x, y, cos theta, right? Intuitively. So the maximum value of this is going to be norm x times norm y. So this happens when cos theta is 1, or both of them are in the same direction. X is equal to alpha times y. And similarly, the lowest value of this arises when cos theta is -1. Okay, so they're in the opposite directions. Okay, so this will be a useful fact, when you devise, strategies for doing optimization. Okay, so yeah, this is kind of sums up about norms and I think about the system of equations. Now, a couple of quick things that I wanted to discuss about eigenvalues and vectors. I think these are things you all know, so we'll just quickly do a recap. So given any square matrix, you have this eigenvalue and eigenvector pair when AV is lambda times V. Okay, so typically we'll say that V is a non-zero vector, and otherwise you're just going to get the null space, right? So V is typically a non-zero vector, and AV is lambda V, and lambda is the eigenvalue, V is the eigenvector. Now, for computing this, I think you would have seen so many times. The way is you just set determinant of A minus lambda I to be 0, and you try to find the values of lambda. Okay, and once you have the values of lambda, what you do is you try to solve this equation. So now, by now you know how to do this, right? Because it's just you want to find the null space of A minus lambda, right? Okay, so even the reason why this determinant is 0, that's because of this fact, right? Like from this, you're just going to get A minus lambda times B is 0. So B lies in the null space of A minus lambda I. So one thing you should also know is the connections between null space and determinants. Okay, so if the null space is if there is something which is non-trivial in the null space, something other than the 0 vector, then what you have is this determinant is 0. Okay, so if a matrix A is full rank, then the determinant A is going to be non-zero. So that is probably something you've already seen. So but this connection with null space is also something you should remember. Okay, so this is the reason why you find the lambdas in this way. Okay, you take the determinant, and this is going to be a polynomial in lambda, and you try to solve the roots of this polynomial. Okay, now some important things you should remember is for a real symmetric matrix, all these eigenvalues that you get, so this polynomial is going to have several roots, and all of them are going to be real when the matrix A is real and symmetric. Okay, now for each of these lambdas, for each of these eigenvalues, you can compute the eigenvectors. And for these real symmetric matrices, the eigenvectors corresponding to different eigenvalues, they are going to be orthogonal. Okay, that's a special property which holds for these special kind of matrices. Okay, so I think these are things you're familiar with, right? Right? Are there any questions on this?
No questions, ma'am.
Okay, good. So what's happening with the rest of you? It's afternoon, I know, and it's a too drab time to be doing math. But yeah, unfortunately, this is the time that's given to us. So are people asleep? Okay, Divya says it's clear. Good. Okay, what about the others? Divya says it's clear. It's clear. Okay. Okay. Okay, that's nice to see. So, okay. So, yeah, so I think we are near the end of the time, but actually today I would like to, wind up with some more things. Otherwise we are going very slow. So if you guys have something else later on, like after this, you're free to move. But for those who have the time, I would like to spend some more time. And anyway, I'll be posting these recordings up. So if somebody is busy with some other meetings or anything, also it's fine. Okay, so maybe I'll just take about 10, 15 minutes more. Okay. So, yeah. So, yeah, these were the things we saw for the eigenvectors and eigenvalues. Now, another thing, a related concept that we have is that of positive semi-definite and positive definite matrices. So a matrix is positive semi-definite if all the eigenvalues are positive, okay, positive or 0, so greater than or equal to 0. And another equivalent characterization is if x transpose ax is greater than or equal to 0 for every x. Okay, so this is actually a quadratic form. Okay, and this is always going to take a value greater than 0. That's what it means. So then you have the other notions, positive definite, if x transpose x is strictly greater than 0 for every x other than the 0 vector. And of course, you have negative semi-definite and negative definite matrices. Okay, and if you could have matrices which are neither of this. So you could have like matrices with positive as well as negative eigenvalues. in which case you would say the matrix is indefinite. Okay. Now, so there are several characterizations of positive semi-definite matrices, and another way to check is this criterion called Sylvester's criterion. So it helps to have like multiple ways to compute this. Okay, by now you would have realized that. So that's what the Sylvester's criterion is doing. A matrix is positive definite if all the leading principal minors are greater than 0. So what are the leading principal minors? So what you do is you start with the first a subset of this matrices. You could take a subset. Okay, so this is positive. Now if you take the first 2 rows and the first 2 columns, okay, so that is this submatrix here, and its determinant, that is the principal minor, and these kind of things, right? Like when you take the first k rows and the first k columns, those are called the leading principal minors. The determinants of those submatrices, those are called the leading principal minors. Okay, so this one is also going to give you 3. Now the final leading principal minor is the first 3 rows and the first 3 columns. Okay, so this is in fact the determinant of the whole matrix. So it turns out that's also positive. Okay, so this is a positive definite matrix. Okay, so this is a condition you could use. Now for the case of positive semi-definite matrices, there's a small difference in the condition. So it's not all the leading principal minors, but it's that all the principal minors take a value which is non-negative. Okay, so what is the difference here? So what you need to do for this case, okay, so this is a matrix with a slight difference. Only these values are -1. So what you should do is you take the first, like all these minors, these cases are there. But in addition, here you take the first and the third row. So you'll also take the first and the third column. Okay. Now you will also, another thing you will do is you take the second and the third row and the second and third column. So this submatrix. So actually in this case, it turns out that all these give you the same minor. Okay, but in general, you should check out all these values if you want to check for positive semi-definiteness. Okay, so here, so all these values are greater than or equal to 0, and that's where it's positive semi-definite. Okay, so yeah, so this brings us to the end of a linear algebra review. Now, one thing I want to also show is about some code snippets. So I've been asking you guys to try out some of these solvers, and in fact, some of the practice questions that I'm going to give you today and tomorrow. That is also going to, I want to make you guys familiar with solvers. So, so I would like to spend some time to just, give you an overview of that. Okay. So before that, any questions till here on these linear algebra concepts? I think it's okay so far.
No questions, ma'am.
No questions. Okay. All right. So I just want to show you, like, coming to these solvers. So there's a solver that I told you yesterday also about Gurobi. Okay. So this is a solver which is quite popular now, and there's been a lot of research, and from where they started, they've come a long way. Okay. It's a commercial solver, but it's open for, it's free for academic institutions. So with your email address, with your IIT Goa email address, you should be able to access these. Okay, and there are a lot of tutorials on Gurobi, and in fact their website, okay, that gives, there's a lot of resources available here, including some modeling examples. So, okay, you should take a look at this. And Gurobi as such, you can call it from several other languages. Like you can invoke it from Python, you can invoke it from C, and so on. Okay, so there are so many examples they've provided, So this is something you should take a look at. So just to give you a very simple snippet. So I'm calling this Gurobi solver from Python. So I'm using this Anaconda navigator. So here what I have is an optimization problem of this form. Okay, so sorry. Yeah. So I have some problem like this: minimize x square plus y square. It's a nonlinear problem such that x minus y equals 1. Okay, and I'm restricting myself to x greater than 0, y greater than 0. So at this point, we haven't really gone into how to solve this. So I just want you to get familiar with coding this up in an optimization solver and invoking the solver. Okay, so so you see this is just very few lines of code here. It's just some 5 lines of code, and that helps you to solve it. Okay, so so I mean you can go over these steps in any of these tutorials. So it begins by by defining a model and including some variables, so you can put in some bound constraints. So this is to say that x is greater than 0 and y is greater than 0. And so this is the constraint that I added, okay? And the objective is this, x squared plus y squared, and I'm minimizing it and call optimize. So this is all there is. So let's just run it. So you see it's quite fast. Okay, it's a small problem only, but you can see some things that it gives. Like this is all the details of the optimization that's going on in the back end. Okay, and this is something called some statistics of the particular method it uses. So it's seeming to use something called a barrier approach. It's an interior programming approach. And these are some other details of the optimization. Okay, so this primal, this is the value it starts with. So it's iteration 0, it's starting with this objective, and it's going on improving this, and till it has found the optimal solution. Okay, so you can see these details, and the optimal objective is 1. So you can also see the values of the optimal variable values, so that you can get by x dot x and y dot x. Okay, so this is a value very close to 0. Okay, so yeah, so you see there's no limit for the way you can use these optimization solvers. You should explore, okay, and try to find good ways of formulating problems and also invoking these solvers. Okay, so the practice questions I'll also expect you to do some of these. Okay, so any questions on this? Okay. So have you used Gurobi? Have any of you guys used any of these solvers in the past?
No, ma'am.
No. Okay. Okay.
And can you show the equation once again?
So this is the one that I was trying to solve.
X and y being x being 0.5 and y being minus 0.5 give a better answer.
But I've enforced y to be greater than 0.
Oh, okay,
Greater
right.
than equal
Sorry.
to 0.
Right. Okay.
Yeah. Okay. So yeah. Any other questions? So use the solver for an assignment in logic. Okay. But was it an optimization problem, Siddharth? Okay. So it's probably to satisfy some constraints, right? That's possibly what you used it in logic.
And for this course, we can use either Python, Matlab, any language of our choice, right?
Yes, you can use any language of your choice. So in fact, if it's the first time you're using these solvers, I encourage you to try even different types, and then you can see for yourself, like, you can compare these solvers and then decide what is a good one. Okay,
Yes.
so in fact, like for some kind of problems like semi-definite programming, second order cone programming, there are some good packages in Matlab. Okay, and for some things Groby is nice. So you should, in general, you should try all these type of solvers. Okay, so any other questions? Okay, so I guess in that case, I think we will break for today. Okay, yeah, so we meet again on Tuesday morning. Okay, so I will, in between, I'll try to check what's up with the class drive folder, and I'll also send you the practice questions. Okay.
Ma'am,
Yes.
how do we access the class drive folder? I couldn't find the link anywhere.
Yeah, Rohit also just mentioned it to me, so I'll just check what's
No, ma'am,
up
I
with
think
that.
he was able to access it. I couldn't even find the link to it.
For the
Oh.
desktop, as ma'am is showing in the Google Drive folder for mobile phones and for tablets, scroll down the menu. There should be a like class drive folders section only. For the
Oh,
for
okay.
desktop computers, it's just this class
Thank you,
tab.
thank you. Okay.
Okay, so for me it shows in this way. So I'll just check the permissions and stuff. So it should be just a simple matter of that. But thanks for bringing it to my notice. Okay, so
Thank you, ma'am.
all right. So thanks everyone. Have a great weekend.
Thank you.
Thank you, ma'am.
Thank you,
Thank you,
ma'am.
ma'am.